Excuse me. So, the general theme of this is tree-based adaptive mesh refinement. Trees are, in this case, not a botanical but a logical structure. Many of you have seen in different contexts throughout your studies. Here, this will include parallel computing algorithms. The parallelism is not something that will change too much how the algorithms are. Most of them will be equally interesting in a serial with just a single computer, no network. But some of those, or most of them actually, generalize really, really well and transparently to parallelism. So it would be a waste if we didn't discuss the parallel extensions, plus such as hugely successful in practice and useful. So this is also, but not primarily on parallel programming. With applications, so once we have some techniques down and at our disposal that are also programmed, at least ideally, as the union of everything that the participants of this lecture do. I have actually, by the way, it's about 13, 14 people. So thanks for your attention and attendance. Actually, we will have some manpower here and woman power, I hope at least, to have some programming that where everybody programs a little thing, and together we will have a bigger thing that actually works. We'll see if we can pull this off. Applications are, of course, solving partial differential equations, such as just the basic Laplace equation, but also you can think of tree structures as a space partition, where space is subdivided in a way that we can manage different subvolumes efficiently. So, for example, any kind of geometry processing, intersections, search objects in space that have some shape and need to be organized or related to each other, can be accelerated by tree data structures. And of course, visualization is one of the prime customers of tree methods for a long time now, maybe even before simulation in a way. So just to repeat some of the topics that are known to people who have seen earlier lectures, it is not necessary to rely on these lectures. This is today just a very brief summary, and over the next 1 or 2 lectures I will make sure all the material everybody needs is here. This will be a slight repetition for those who've seen some past lectures of mine, but hopefully it's still a little interesting, and for the others, of course, it will be necessary to get into the flow of how I'm presenting and arranging the material for this course. So 1.1 is about how to subdivide a domain in space. So suppose we have the real numbers to the power of d, the space dimension. The first subdivision is taking the domain and trying to divide it into, for example, 2-dimensional cubes here that are indexed in some unreadable way in this picture. I will call these blocks, which is a term commonly accepted in practice, numbered with k. My numbers begin with 0 and go to big K exclusive. That's why I'm taking a round parenthesis here. We will, each of these logical cubes have to be images of an actual cube. So we call this the reference cube, and each one is the image under a map that I index with the block number 0, in this case for K0 and 2 for K2. So you see this map here. The union of these cubes is supposed to compose the whole domain. So if you have curved boundaries and multi-block intersections or actually interfaces, then I expect the transforms to be compatible, so we don't have overlaps and non-trivial intersections and holes and cuts and whatever. So I'm not saying how this can be done, maybe a little bit, but this is more of an assumption of structure. Suppose we have these multiple blocks, we would try to refine into elements of smaller size. It is really convenient to divide a domain of a non-trivial shape into several blocks to capture the basic topology and geometry of this object. But having each element of individual shape also requires expensive encoding of this shape. So we may want to save on geometry parameters by, representing each block with its own geometry that is parameterized in a possibly expansive way, maybe having high order polynomials or some splines of high degree and so on. But then the whole block is encoded with the geometry of one block is encoded with this set of parameters. And if I subdivide the block into multiple smaller pieces, all of these inherit the block geometry, so we don't need extra storage of geometry parameters per element. We only need them per block, which is quite economic if we refine to, say, a constant number of blocks, but a lot of subdivisions within each block. If I subdivide adaptively, this is an example of 2 blocks in 2 dimensions, so those are logical squares, again, glued together in the middle. We see that we can subdivide here in some non-uniform way. For example, having these little squares and squares within little squares. This is adaptive in the sense that we can refine wherever we need accuracy. If you remember your approximation theory classes, the accuracy of interpolation, of projection, of approximation in general increases if we take smaller subdivisions, often called h as a characteristical length. So wherever we expect to wherever we think we want to be more accurate, we would subdivide locally, but not in some places where accuracy is sufficient already. So this means the subdivision is now non-uniform. Especially this means that different blocks have different refinements. So each block has its own refinement structure. For the purpose of the presentation here, it's enough for now to consider just one block and see how it works there, and later we can combine multiple blocks into the whole domain. So this is an example, figure 1.4. Suppose we begin by tracking our contents here, tree-based adaptivity. We begin with a single two-dimensional block. This is just, if I number all the elements in the block, this is number 0. And we call this the root of the tree. Let us subdivide this block by halving it in each dimension. We get, in 2 dimensions, 4 elements numbered 0, 1, 2, and 3 in some order that I just made up here. And this means we get the first refinement level of this tree, which for now looks uniform still. Suppose we would continue this scheme, though. We can take element number 0 in this middle row, subdivide it, and then we can take element number 3 in this middle row and subdivide it. If 0 and 3 are the outside elements in this sequence that we chose, then refining creates additional subtrees below the first set of elements 0 and 3. You can continue numbering them in a way that the numbering of these original divided elements is respected, in the sense that all the elements that are below the original element 0 come before the original element 1. And all the elements that are now below in the hierarchy element previously 3, all are later than all the elements that are derived from the previous element number 2. Which means we basically count the elements left to right in this tree if you follow the mouse pointer. So one block is one tree. In this representation in 2D we call it a quad tree, since we have 4 children. In 3D it's called an octree, a very famous structure that has been around especially in graphics since well, way before I was actually thinking about these things. So the ordering, of course, is somewhat arbitrary. If we, I have put down a couple examples here in figure 1.5. You see that this is going left, right, and then top, left, and right. We could just go around clockwise here, or maybe counterclockwise if we want to. So what's best? Depends on various things. We'll look into this. Of course, I have a preference, basically because of the focus of this lecture, and that focus is a specific choice called linear octree. How will we get there? So from one refinement to the next, we choose lexicographic ordering. This is a choice. Again, there are multiple different ones. many actually that people have tried. What does lexicographic mean? It's Greek, obviously. Lexico has something to do with to read, or a book is also the Greek word. Graphic has something to do with writing. I look at this as a right-handed coordinate system. If you take the axes as the sequence in which you would read a book, first you read the line, then you read down the lines on the page, and then you turn the pages as the z direction. We will naturally get a right-handed coordinate system, which is really quite convenient, and nobody knows if this is intentional. Historically, probably not. And then we can repeat this recursively. So what this means here in this figure, if I'm being too fast, actually, just let me know. I get the feeling that at this speed, it will be impossible for you to write down even half of this. So instead of you always pausing the video, maybe I should put in some redundancy in the file and allow for breaks. I'm just curious on your feedback, please. So let me know how the speed is. I will now switch to a slower speed, and you have a comparison and can let me know what you think. For now, by email, later by chat protocol, or maybe even later by real-time comments. So if you look at this three-dimensional picture here, this time with the origin in the bottom left front, we see that I try to be lexicographic in this the same coordinate system as above. It's just rotated over to have the origin right here in the lower left front. And I'm just marking the elements in this numbering. 0, 1, 2 is the bottom back left, and 3. And then when I'm done with x and y, I go up in the z direction. Go to number 4, 5, 6, and 7. I hope this is understandable, this picture. So depending on the space dimension, I always get 2 to the power of d children for each element. And then if I choose to refine an element, I do the same thing at a scale of 1/2 lower. In 2D, I will do this twice, actually. So the number of steps from the root to the next level is called level in a way, right? So we begin with the root and define it as level 0. The next set of children would be level 1. And so on. Level 2 would be the second iteration of this recursion rule. Interestingly, now if we say we go down to level 2, we could know already that the x and y steps in our coordinates are quarters, 4 being 1 over 2 to the power of d. And if we also encode the number of the child in our lexicographic ordering, in 2D it would be 0, 1, 2, and 3, we can write this down as base 2 numbers, binary digits, 0, 0, 0, 1, 1, 0, and 1, 1, which happens to be 3, the last one. The last number in a zero-based counting is always the total count minus 1. And then suppose we do this on every level again, which means whenever we go down one level, we add 2 binary digits in 2 dimensions, 3 binary digits in 3 dimensions. If we do this here, this element is a special one. I just marked it in black shade here. So first we have to go down to element number 1 on level 1, and then we have to go down to the child number 3 of that element number 1. So we can take the 0, 1 identifier and then the 1, 1 identifier, and that uniquely defines which element we're looking at. We could just take them here. 0, 1 was the first one. 1, 1 was the second one. See it as 4 binary digits. In fact, we could convert it into decimal again. We get 7. 7 makes sense. Why? Because we basically count on the finest possible level 2 in this example. 0, 1, 2, and 3, 4, 5, 6, and 7. So this is zero-based number 7, binary 1, 1, 1 in binary system. So far, so easy. The tricks begin only now, actually. So if you happen to grab just every other element, in this case the left element of each pair of refinement, then we notice that the left element basically tells us if we are in the low half or in the top half, or here in the lower half of this or in the top half. So if we take this binary, convert it into number, we happen to get the y-coordinate of the point. So if you count the coordinates in multiples of 1/4, 4 being 2 to the power of maximum level, this x-coordinate is actually 3 and the y-coordinate is 1, which we got here. If we take the other item of each hierarchy descriptor, we get a 1, 1, which really is, this is the x-coordinate 3, as you can see, 0, 1, 2, 3/4 here. So the element coordinates are 1/4, which is 2 to the power of max level 3, 1 in x and y. So that's the first thing that not everybody has known, I would think, about how we can encode such an octree. It is in a sense the simplest possible, since we have such a clear separation between the different coordinate directions. Everything is entirely dimension independent. We could do this in 16 or 78 dimensions. Of course, we don't have the memory for it, but the coding principle is the exact same, which makes this super quick to actually program and to run. I'm getting to my last summary slide for today. We see that we can modify elements. We could basically move an element one step to the left. How would we do this? We would subtract h from the x coordinate. What is h? H is 2 to the power of the number of levels relative to the root level. So the h of an element of level little l is 2 to the power of big L minus L, where big L is some number that we just say is the maximum we choose of refinement. So we could say maximum level is 18, just because we think that's deep enough. Then we would have 18 bits per coordinate in 3D. That gives us 54 bits. So if we wanted to use, for example, 64 bits, we could go a little deeper still. Which means also that each element is uniquely identified by its level little l and the lower left coordinate, in reference to the previous slide on encoding. So if we have x, y, z numbers and a level here, we can rearrange the bits with the scheme from the previous slide, taking the highest order bits, z, y, x, then the next highest bits, that would be index L minus 2, big L minus 2, z, y, x, down to the least significant bits, z, y, x. The index here is the number of bits from the right. So index 0 means the rightmost bit. Index 1 would mean the bit that corresponds to 2 to the power of 1. Bit number 2 would correspond to 2 to the power of 2. The level needs to be appended, since elements of multiple of different sizes can have the same x, y, z coordinates of the lower left corner. We need to know what size we're looking at in addition. This bit string here, let me call this big I of x, y, z. And again, these indices here are just the bitwise encoded strings of the respective coordinates, which are in the smallest possible length of an element is 2 to the power of minus big L. So with the scaling factor 2 to the power of L and x between 0 and 1, we can encode it discretely as integers. So there is no round-off error, no floating point numbers, no real numbers. This is a completely integer-based representation. What are element level algorithms? That's our topic here in this 1.4 summary section. Suppose we want to know if some xyz coordinate is actually a valid pair for a certain level. Not every coordinate is possible to be assumed by an element of a certain size. If you just think of the root quadrant, the only possible way for its coordinate is to be 0, 0, and 0. So if we were saying we have a level 0 element with a coordinate 1/4, 3/8, and 5/16, that would not be possible. Such an element would be invalid. We need to figure out what elements can possibly be valid, and the answer is simple in that each coordinate must be an integer multiple of the size of the element. That's all, actually. In binary, this can be encoded with bitwise AND operations. So if I construct, what do I need to say, basically? If an element is the multiple of its size, the size itself is here, 2 to the power of big L minus little l in integer coordinates. Which means that multiples of that, so this h has a representation as a binary number. It's a 1 with big L minus l zeros. So multiples of that will preserve those zeros, which means the 1 starting at bits big L minus little l can be multiplied into any kind of number which populates the bits to the high significant side, but the low significant side must be 0. So if I want to construct a number that is all ones up to a certain bit, I take the power of 2 and subtract 1. It's the same as having a number 1000, subtracting 1, and we get 999, which is in a decimal system the highest possible digit in all places to the right. So in base 2, the highest possible digit is 1. If we take 2 to the power of something, subtract 1, we get a whole string of highest possible digits from the left to the right. So we're demanding that all these bits must be 0 for an x coordinate to be valid, and it holds independently for y and z. So this is our first element level algorithm. It's just a function that says, is this combination valid? Of course, I'm inputting I, but I'm asking for x, y, z. This is only possible if I of x, y, z is a bijection, which in this scheme clearly is the case. Multiple other fun algorithms. How would you, just based on the bit description, construct a parent, construct a child, or ask if one element is actually derived from another by subdivision, or if it's actually bigger, or if it's unrelated? Those are the 3 possible cases. So this would be another fun function. So my idea for now is that over this first half of the lecture, everybody writes one of those, say, 6 or 7 or 8 functions, and we have a little library of functions that we can use to question the status of elements. So those are building blocks for whatever comes next, 1.5. So after the element local algorithms, we will look into global algorithms where relations of the whole mesh in terms of which element has any impact logically on other elements, or how do neighbor elements relate, how do parent and child elements relate, how do I actually create a subdivision, how do I do the reverse, meaning coarsening, removing a subdivision, going back up the tree, which may be necessary if I end up with less accuracy requirement than before. So I think I'll stop my recording here. We will have a group chat session, I would think a couple of days after Monday, maybe on a Wednesday or Tuesday. I'll put some suggestions up on the web page. Again, the material will be uploaded. In this group chat session, I'll be very curious on your feedback on this lecture, or the first attempt at one such lecture, and I'll try to incorporate all of that into future sessions. Other than that, I'll try to get eCampus rolling. Right now, I'll just put this into some hosting service where I can send you some kind of cryptic link. But of course, I want to do this with eCampus. I want to do this with SIBO and so on. But right now, I'm just not fully set up doing that. So apologies if this is all a little shady still, but we're getting there. So thanks a lot. I hope to see you in a couple of days, or see, who knows, if we can actually stream this chat session. We'll work on that. So stay tuned, and I'll update you more on on the web page.